Istanbul. For more than 2,000 years, it stood at the crossroads between East and West. The point where Europe ends and Asia begins. The two continents divided by the Bosphorus Straits. This is one of the great journeys. Stepping off the continent and leaving Europe behind. But crossing the Bosphorus isn't all that it seems. This notion that Europe and Asia are separate is a bit of a nonsense. From a geological perspective, they're both part of the same vast landmass, Eurasia. Stretches from the Atlantic coast of Portugal all the way through to Russia's Pacific coast, making it the biggest continent on the planet. To reveal how this mighty continent formed, I want to reach back in time. Because if you know where to look, there are clues to its ancient past written into the world around us. Its landscapes, wildlife. Hey, is that ketamine? And the very rock from which it's built. The tiniest detail can reveal the history of a vast continent. Evidence that shows how Eurasia was assembled in a series of monumental collisions.
It's just kicked off just as we got here.
Catastrophic impacts that created the conditions for civilizations to rise. Changed the course of life on Earth. And left an indelible mark on the landscape.
Just a wall of rock and ice.
A mountain range spanning the entire continent. And the story of how that formed is the story of how Eurasia formed. A continent forged in a series of collisions that continue to this day. And because the process that built Eurasia is still active, the largest continent on the planet is merely the start of something far bigger. The first clue to uncovering Eurasia's past can be found here in Istanbul. For centuries, the city's strategic location at the heart of the continent has made it a major centre for trade.
It's Turkish delight.
Love.
With honey and pistachios, no sugar. Yes, honey and pistachios. It's lovely.
Just as it does to this day.
We can't waste it for your mother-in-law.
There's a joke there, I'm sure. I mean, that's the thing about these bazaars. They still sell the traditional things that they've been selling since this city was in its infancy. Look at this. I mean, exotic foods there, spices, metals, spice men, jewellery, precious stones like this, ceramics. If you want it, it's here.
Can I smell, please?
Wow.
But there's one product that's shaped Istanbul's history like no other.
In a way, this city is here because of this stuff. Silk. Look at it, it's just gorgeous. If you go back to the 6th century, this is one of the most expensive, most sought-after commodities. Partly because it comes all the way from China, and also because how it was made was this closely guarded secret. The story goes that a delegation of monks would smuggle back a couple of silkworm inside a bamboo cane, brought it back here, and in this place, Istanbul, just
took off as a kind of hub of silk production.
And the fabric gave its name to the Silk Road, the network of ancient trade routes that runs across the entire continent, connecting China through Istanbul and onto Europe. And the Silk Road is crucial to the story of Eurasia today, because beneath it lies evidence that reveals the origin of the continent itself. Evidence that can be found 500 kilometres southeast of Istanbul, where the Taurus Mountains reach the shores of the Mediterranean. In a place that's been both a staging post on the Silk Road and a site of pilgrimage since the days of ancient Greece.
This whole landscape is steeped in myth. I mean, just over the back is Mount Olympus, the home of the Greek gods. Actually, it's one of about 20 Mount Olympuses that's scattered across the ancient world. But the mountain that I'm climbing now is unique, Mount Chimera. It's named after this mythological creature that's got the tail of a snake, the body of a goat, and a lion's head. Oh yeah, and it breathes fire. These are the eternal flames. In Turkish, they're called yanartaş, which is just flaming rock. Look at them. I mean, today they're maybe half a metre high, but in ancient times they were much higher. So that if you're out at sea, you could see this place as a lighthouse. But my favourite story, though, is because we're so close to Olympus, this could be the source of the first Olympic flame. It's such a surreal scene.
But what fuels these flames is far more ancient. And analysing it takes you back tens of millions of years to the time Eurasia formed.
Fossilized sea creatures, plankton, 3 to 4 kilometres into the air. Do you see this black residue here? It's soot, essentially carbon. And that tells us that these flames are burning an organic compound. In this case, natural gas or methane. And geochemical analysis of these flames indicates that that gas is coming from carbon-rich rocks deep underground. Much of it from fossilized sea creatures, plankton. To transform plankton into gas, you have to take the long-chain hydrocarbons that make up the cells, and you have to break them into smaller and lighter bits.
This process happens spontaneously at around 140 degrees. Temperatures that can be generated by burying the rock 3 to 4 kilometres down into the earth.
The best way to do that is to pile layer upon layer upon layer of sediment on top of it. And the place where that process happens all the time is the bottom of the deep ocean.
The gas here shows that millions of years ago, this region of Turkey was underwater. But the evidence of a lost ocean doesn't stop there. It can be found all along the ancient Silk Road.
This is Eurasia as we know it today.
And here we are, down here in southern Turkey. Some of the biggest oil and gas fields on the planet occur east of Turkey in a belt through Central Asia to Afghanistan. But east and west of that too, there's evidence of a former ocean. There's precious stones that started off as rocks on the ocean floor, things like jade, which occur in Pakistan, occur in Burma and in China, and then marble that occurs in Greece, Italy, and other parts of Europe. You also get metals that are formed on the bottom of the ocean, metals like copper that you get found in Cyprus. But the final evidence, the best evidence, is fragments of the rock that I'm sitting on. These are fragments of ophiolite, ancient ocean crust, which you find formed in a kind of belt all the way across this region. What all these lines of evidence add up to is the fact that there was once a vast ocean that stretched the entire length of this continent.
The continent of Eurasia as we know it today didn't exist 200 million years ago. Where the south of the continent, Italy, Arabia and India are today, there was a 90 million square kilometre ocean. The Tethys. Western Europe was lost beneath its waves. And Britain was a collection of tropical islands off its northwestern shores. Wrapped around its long arcing coastline, all the Earth's land masses were joined together into one vast supercontinent. Called Pangaea, it was a land dominated by the dinosaurs. Just as fearsome marine reptiles ruled the Tethys.
Today, all those creatures are now extinct, and the Tethys Ocean itself is long since disappeared. But what destroyed the Tethys and led to the extinction of many of the creatures that lived in it is the same geological process that led to the formation of Eurasia. Because the story of Eurasia is essentially the story of how the Tethys died.
The mystery of how Eurasia formed from the death of the Tethys involves one of the greatest mass extinctions in Earth's history, the rise of its ancient civilizations, and will reveal the continent's ultimate fate. And clues to how that happened can be found in the southernmost tip of India.
These are the gentle backwaters of Kerala in southern India, a place famed for its spices, especially black pepper, and one of the key staging posts on another of those ancient trading routes that crisscrossed Eurasia.
For centuries, Kerala's lakes and waterways have supported a traditional way of life, a floating existence that still survives to this day.
But I'm here to find something truly ancient, something that's lived in waters like these for over 100 million years.
A creature that provides a direct link back to the most important event in the formation of Eurasia. And is, for the local fishermen, these waters' most prized catch. A fish known here as caramine.
Hello. Hi.
Hello, hello, hi.
Hi there. Hi there. So caramine is tasty. Very, very tasty. Is there a lot? Is it all over? All over. So how do you catch it? You jump in?
Catch it.
You make it sound so easy.
First, two of the fishermen use a line to scare the fish into the mud at the bottom of the lake. Then the others swim behind, making a noise to startle the fish. Before plucking them from the mud with their bare hands.
Yay! Is that caramine? Yay! Fantastic. Number one. That's fast. Very nice. But this is it. This is what all the action was for. A caramine. Latin name, Etriplis suratensis.
A fish whose anatomy reveals the evolution of entire continents.
The anal fin. Shape of the skull. It's a type of fish called a cichlid. They're marked out by a couple of anatomical quirks that make them distinctive. One of them is right at the back. It's at his rear end, basically, the anal fin.
Now, in most cichlids, the anal fin's got 3 or 4 spines. But this species has many more.
And the other characteristic is at the front end, it's in the distinctive shape of the skull, which relates to the swim bladder, that sac that controls the buoyancy of the fish.
There's only one other group of fish that share these distinctive characteristics. The closely related Etriplis cichlids. And they live over 4,000 kilometres away in Madagascar.
Now, Etriplis can tolerate slightly salty conditions, but they're essentially a freshwater fish. So one thing's for sure is they didn't swim here. Instead, the answer is that it's not the fish that moved. It was India. This is a reconstruction of how the Earth's land masses looked like 120 million years ago, just before the emergence of the first cichlid fishes. You can see up here, China and Siberia fused together, and you can see the area here that's going to become Britain. And this, in here in blue, is the Tethys Ocean. And down here, past the equator into the southern hemisphere, tucked snugly in beside Madagascar, is India. And if I press play here, I can simulate how the land masses then move. And what you find is that 90 million years, India and Madagascar split.
Then suddenly, 25 million years after they separated, India more than doubled its speed.
I mean, that's dramatic stuff. That's a mini continent, something like 3,000 kilometres across, just speeding across the globe, crashing into Eurasia. It's fantastic. I never tire of watching that. It's great.
India's journey north was a key moment in the formation of Eurasia. Because as it moved, it closed the ocean in front of it, spelling the beginning of the end for the Tethys. But the big question is what caused it to speed up? because that led to one of the most catastrophic events in Earth's history. And you can see evidence of that cataclysm in the hills outside Mumbai, a place known as the Deccan Traps. The Deccan. It's one of those words for a geologist that conjures up these images of this iconic landscape, stepped plateaus and things. And yet, this kind of gentle landscape holds in it one of the cataclysmic geological events in the planet's past. But there's telltale signs in that cliff face there. You see, it looks like a set of bands. They're layers of lava, molten rock that came out, solidified, and then built up layer upon layer upon layer over tens, hundreds of thousands of years to form these hills. 68 million years ago, this landscape was very different. Eruption after eruption poured 1.3 million cubic kilometres of lava across southern India. Enough to cover the UK in a layer of rock 5 kilometres thick. All over these hills there's gems like these just carved into the lava. But there is no volcanic activity in India today. So the question is, where's the source of these eruptions? And how did it speed India up? This whole cave is carved out of a type of lava called basalt. Ilmenite, magnetite, latitude. It's got really fine crystals. About 10% are minerals called iron oxides, rust. It gives us this reddy, browny tint. Minerals like ilmenite and magnetite. And that's the clue, because these iron oxides are magnetic. Just after the lava solidifies, its temperature drops below 585 degrees, and the magnetic fields of the iron oxide crystals align themselves with the planet's own field. Now, the thing about the Earth's magnetic field is that it changes depending on your position on the planet, where you are between the South Pole and the North Pole. In other words, your latitude. It's a property known as its inclination, and it means that the basalt contains a record of its position at the precise moment it solidified, which allows you to pinpoint exactly where it formed. Today this temple's at a latitude of 18.7 degrees north. But the thing is, the magnetic inclination of the rock itself tells us that it formed at a latitude of about 20 degrees south. In other words, this lava formed in the southern hemisphere. So the thing is that the source of this volcanism isn't to be found deep beneath my feet here. Instead, it's several thousand kilometres in that direction. If you trace India's journey back to the point it crossed 20 degrees south, you arrive directly over a mantle plume. A huge column of superheated rock that rises up from near the Earth's core. As India moved over the plume, it triggered the Deccan eruptions. But deep underground, it had another impact. Something that can explain India's dramatic acceleration. Continents floor on the mantle like vast ships.
just as the hull of a ship lies below the waterline. So the bulk of a continent, maybe 80% of it, extends deep into the earth. Today, the Indian continent's half the thickness of the other great land masses. It's thought that that's because as the Indian plate moved across that mantle plume, it melted away at the base of the continental plate. According to that idea, that huge loss of mass combined with the lubricating effect of that molten rock and also maybe an extra push from the mantle plume caused India to double its speed, propelling it towards Eurasia.
It was a geological cataclysm. But the implications for life were even more dramatic. Because the Deccan eruptions contributed to one of the greatest turning points in the history of life on Earth. As the plume burnt its way up through the continent, it pumped billions of tons of ash and toxic gas directly into the atmosphere. Over hundreds of thousands of years, this slowly choked the planet and poisoned the oceans, wiping out 50% of all life. And for the dinosaurs, it led to a drawn-out decline, until it's thought an asteroid finally finished them off. But the end of the dinosaurs turned out to be our gain, because as one group of animals died out, so another rose to take their place. The mammals.
In a way, the extinction was curiously selective. I mean, you and I would never have survived. In fact, no land vertebrate larger than 25 kilograms made it through.
But back then, our distant ancestors had just the right mix of characteristics to survive. And there's one modern mammal that's thought to have similar adaptations today. Because what's worked in the past also works in the mean streets of Mumbai.
वैसे देखा जाएगा तो चूहे ज़्यादा बहुत ज़्यादा है चूहे मुंबई में और पब्लिक से ज़्यादा चूहे लोग हैं.
The city is such a large rat problem, it employs a small army of rat catchers, like Rakesh Dadji Missile.
अच्छा लगता है लेकिन बुरा भी लगता है उसके वो सच है क्योंकि जान लेना पड़ता है चूहे का. तो क्या पेट के लिए कुछ भी करना पड़ता है ना इसकी वजह से. ऐसा देखा जाएगा तो अभी के हिसाब से चूहे ही जीत रहे हैं क्योंकि उतना जितना उनको मारो उसके डबल उनकी पैदावार हो रही है.
So anyway, think of humans as being the most successful mammal, but I reckon we're looking at the ultimate one here, rats. I mean, they've certainly got all the essential traits for survival. They're small enough they can get into nooks and crannies and just keep themselves tucked away from harm. And then food, they're voracious eaters, eat anything. And that not having to rely on a single source of food, it's really useful. And I guess the main thing is sex. I mean, these things breed like rats, really, which is why the rat catchers of Mumbai are struggling to keep up. You know, if it's a question of who's going to survive the next apocalypse, my money's on them.
It's curious to think that it might have been characteristics possessed by the humble rat that enabled our distant ancestors to survive where the dinosaurs had perished. And that it was the movement of India that ultimately paved the way for us to inherit the earth. As it continued north, India left the mantle plume behind. But now travelling twice as fast, it crashed into the rest of Eurasia. Changing the face of the continent and sealing the fate of the Tethys Ocean. But the demise of the Tethys would have another major impact on human history, shaping the rise of Eurasia's civilizations.
Morning, Max.
Hello, sir.
Hey!
Welcome on the board.
Welcome, yeah. It's small, isn't it?
To see how that lost ocean influenced our past and still affects us today, you need to take a closer look at the most obvious result of the collision.
Yeah.
Where's the music coming from? Where's your tape deck? Your CDs? Ah! I love the music, I just can't get over the music. Giorgio Moroder. Lovely. What a place you have here. It's a long way down. It's a very, very long way down.
These are the Himalayas, the greatest mountain range on Earth.
Oh, now we're seeing the mountains. Here they are. The Dalagari's over there, Mansu's over here, and Annapurna's ahead of us. All three of those are over 8,000 metres, 26,500 feet. That's 3 of the top 10 mountains in the world.
The mountains look solid and immovable.
Ah, that's majestic. Just a wall of rock and ice.
But that is just an illusion. These peaks are in fact a slow-motion car crash playing out over millions of years.
And still we climb. It's absolutely stunningly beautiful, but when you look at the mountains, as a geologist, you see so much more. It's almost like you see through the obvious snow and rock to the inner workings. You can see the process of mountain building almost in action. Oh, I can see some folds. So Max, that's those folds up there. You can see the rocks kind of wrapped around this enormous fold structure. You can see there how that there comes across, swings down, and then back. It's a big Z shape. It's not just the shape of them that's spectacular, it's the sheer size. See these Zs up there, Z. We call them Z-shaped folds. It's very technical, George.
These folds, some the size of entire mountains, were created as India ploughed into the rest of the continent. The immense power of the collision, twisting and contorting solid rock as if it were plasticine.
Ah, yeah. I love it. Love it.
You might think these contorted rocks are pieces of the land, scrunched upwards as the two continents ploughed into each other. But the reality is far more surprising.
This is one of the great rivers of Eurasia, the Kali Gandaki. It starts up there in the north in Tibet and flows down through the wilds of Mustang province in northern Nepal, down through here to India in the south. For millions of years it's been carving its way down through the Himalayas to produce what down there is one of the deepest gorges in the world.
And it's in rivers like these that you can find clues to the origin of the rock from which these mountains are formed. Curious stones, called salagrams by the locals, who worship them as manifestations of the Hindu god Vishnu.
What I'm looking for is hard black nodules, kind of black lumps of shale that's fallen out the cliff and then been washed around. And I'm hoping that at the heart of one of these nodules, we're going to find a salagram, because often they enclose them. You need to break them open and reveal them. And what's lovely is that when you reveal them, if you get it, you're exposing something that last lived in the Jurassic, 100-odd million years ago, sort of exposed back to the world. And the other thing that's lovely, if you find one, is you're the first person in the world to ever find that. Because it's been hidden away for hundreds of millions, 100 million years or so, and then you break it open. It's your fossil. So if you see any, tell me. You're looking for a natural weakness, and once you get that, this will be the one. This will be the one. This geology lap's harder than it looks. I mean, the funny thing about it is all the way up that road, there's guys selling these things. Get them from the rock and they sell them to all the tourists. And I thought, no, 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 no. I'm going to find them for real. How much for this? How much? That's
350.
350 rupees. Okay, one. This is going to be a bargain. 300. This 300. Okay.
Okay.
Okay. Now this is a salagram. Look at that. Absolutely beautiful. Geologists know it better as an ammonite, and it's the fossilised remains of an extinct member of the squid family. The modern day version would be the nautilus. The body would be in here, and the head and tentacles would sit out here. And the thing is, just like the modern day nautilus, these creatures didn't live in the mountains. They lived in the ocean. That's the thing about geology. It's not really the rocks themselves that are important. I mean, this is a rather boring black mud, but it's the stories they tell. I mean, these ammonites were swimming around in Jurassic seas when dinosaurs roamed the land, when Eurasia was really coming together. That's what the story of the rocks tell.
The walls of this valley, 2,700 metres above sea level, are brimming with the remains of ancient sea creatures.
Marine fossils have been found right across the Himalaya, including right at the top of Mount Everest. It's astonishing to think that rocks that started out at the bottom of the Tethys Ocean are now the roof of the world.
When India collided with Eurasia, the ocean floor at the margins of the Tethys was thrust upwards, forming an immense barrier across the continent. And it's by creating that barrier that the Tethys has had a profound effect on the course of human history, and still does to this day. Because mountains this high can't help but interfere with the climate.
That is one angry sky up there, isn't it? That's the thing about mountains, they create their own weather, and the bigger they are, the bigger the weather they create. And somewhere behind that cloud and mist is the Himalayas, the biggest on the planet. So it's no real surprise then that it produces one of the most important weather systems on the planet, the monsoon. The winds that bring the moist air rise up along these slopes and just dump rain and snow on those hills, and you get these brutal downpours like these that kind of running up to the wet season that dump water in the gorges and rivers up there, creates mudslides and landslides that just chuck it down, chuck material. If you can just see, there's a river down there that's flooded, that's just full of mud and dirt that's been taken out of that mountain range. This is one of the most dynamic, active environments in the world, and also one of the wettest.
These sediment-laden waters flow down from the mountains and out onto the plains of India, Pakistan and China. And combined with the monsoon rains, water and nutrient-rich soils from the Himalayas support 3 billion people. Nearly half the world's population. But the formation of Eurasia has had a much wider impact on civilization. Because India's collision was only the beginning of the end for the Tethys. Arabia also moved north, creating the Zagros and Taurus mountains that run through Iran and Turkey. Italy and Greece collided with northern Europe, building the Alps and completing a mountain chain that spans the entire length of Eurasia and marks the final resting place of the once great Tethys Ocean. And just as the Himalayas support Asia's population today, so this immense chain of mountains created the conditions for the first civilizations to rise across the continent.
Oh, wow, look at that. Isn't that magnificent? Many of the great Eurasian civilizations sprung up in the shadow of the mountain chains that spanned the continent. They occupied fertile river valleys that grew up on the back of sediment and water washed down from the mountains.
Following the line of the mountains and connected by trade routes, a chain of empires developed across the continent. But the mountains themselves also provided a sanctuary for numerous city-states, like the obsidian city of Termessos in the Taurus mountains of southern Turkey.
If you're a society that lived in the mountains, then you had to work with the geological cards you've been dealt. This is a fragmented landscape. Cities like this are physically hemmed in and isolated from their neighbours. But isolation also means independence. And cities like this could become crucibles of invention and innovation. Empires like the Greeks and the Romans that had mountains at their heart became successful because they were able to harness that ingenuity.
So in a way, Eurasia's long history of civilization goes back not thousands, but millions of years, to the formation of the mountains at the heart of the continent. Eurasia as we know it was complete around 20 million years ago. The land masses that formed it had moved into their current positions. And with the closing of the Tethys, Western Europe, including Britain, emerged from beneath the waves. But the formation of Eurasia is really just the beginning of the story, because the process that built it is still active today. And by understanding that process, it's possible to chart the astonishing future that awaits the continent.
This is the Mediterranean Sea, instantly recognizable on a map. On the west, it connects to the Atlantic Ocean through the narrow Straits of Gibraltar, and then in the east, it's the shores of Turkey and the Middle East that end.
But just like the Tethys before it, the Med too is closing, as the vast African plate moves north. And where it collides with Eurasia beneath the southern tip of Italy, it's created a cluster of volcanoes that rise up from the ocean floor.
This is Stromboli. It's actually the solidified throat of an ancient volcano. 200,000 years ago, that rock was molten, rising up to spew and explode out of a volcano that would have risen above our heads. And then around that time, that volcanic activity switched to the south, and this thing just crumbled and collapsed back down into the seas. So that all that's left is this solid volcanic neck, the innards, the guts of an ancient volcano.
Today, the tiny island of Stromboli lies 2 kilometers north of Stromboli. Italy's most continually active volcano.
Look at that.
And a place you can see Eurasia's destiny taking shape.
The thing about volcanoes is that they're windows into the inner earth. And this particular one's a window into the most important process driving the movement of the continent. The only trouble is that to understand it, I have to get right up there.
The summit towers some 900 meters above sea level, casting a long shadow over the island and the villages that cling to its shores.
Look at it steaming away. Oh, that's perfect. It's just kicked off just as we got here. They call it puffing here. A big puff, and you can see all the boulders just rolling down the hill in the smoke there. God. We've arrived. Whoa, hey! Look at that. That's Stromboli for you. Isn't that magnificent? This volcano has been doing this, exploding like this every 10, 20 minutes really for the last 2,000 years. Whoa! That's a goodie. That's a cracker. It's so hard to get an idea of the intensity of that, but those orange balls that are getting kicked out there are actually metre-sized boulders. And the temperature of that must be 500, 600 degrees. Extraordinary. You really don't want to be much closer than this. Well, I do, but... What makes Stromboli special is it doesn't really produce that much lava. I mean, unlike volcanoes like Hawaii and Etna that spew out these huge lava flows, this volcano's eruptions are almost exclusively explosive. And at night, when the sun goes down and the fireworks really start, you really understand why it's called the lighthouse of the Mediterranean.
Stromboli's regular explosive eruptions create one of the planet's most astonishing spectacles. But more than that, they're a clue to understanding the process shaping the fate of the continent.
Viscous and sticky, trapped gases, so explosive. The Teth is destroying itself. This crater rim is just littered with blocks that have been thrown out of that vent down there. Stuff like that. I mean, this material is actually made of a rock called andesite. Andesite is quite a light grey rock, and that's because it's got a lot of silica in it. And because it's got a fair amount of silica in it, it tends to make the magma quite sticky and viscous. And that means it traps gases. There's just lots and lots of bubbles in this rock. And it turns out that it's those bubbles that's the reason why those eruptions are so explosive.
As the magma rises to the surface, the gas trapped inside expands until the bubbles burst and the rock explodes. But the gas responsible isn't one you'd immediately associate with a volcano. It's water vapor or steam.
This rock actually explains where the water comes from to drive those steam eruptions. Now, you might think that the steam comes from seawater sinking into the volcano, but actually the water's already in the rock. Look at this. This is an andesite without all those bubbles, so that you can see all the beautiful crystals called pyroxene.
Pyroxene crystals form at depths of 5 to 10 kilometres. And as they grow, they encase tiny quantities of magma, locking it away and carrying it up to the surface.
Now, if you could look into those tiny specks of the original magma that formed this rock, you'd find that there was water in them. In other words, the water was actually in the magma, deep down in the mantle.
The only way water could be found so deep in the inner earth was if something carried it there. In this case, it was dragged down in the rock that forms the ocean floor itself. Because Stromboli is a volcano powered by a process called subduction.
Subduction generally happens when ocean crust meets continental crust. Now, the ocean crust rocks are denser, so they sit lower on the mantle. And when they collide, the ocean crust gets pushed underneath the lighter continental crust, descending down into the mantle. So that eruption up there actually started off about 100 kilometres beneath our feet. Down there, water gets forced out of those ocean rocks and causes the rocks around them to melt, which rise up and eventually bursts out as volcanoes.
Subduction is the ultimate fate of all ocean crust. But it isn't a consequence of the continents moving. Subduction is the engine that drives their movement in the first place.
As the ocean crust descends beneath the continental crust, it doesn't break off. It's still attached to all that ocean floor. And it's that vast slab of rock heading down into the mantle that pulls the ocean crust and in turn hauls the land masses behind it, dragging the continents across the face of the earth. Maybe it's because we live in the land that it's tempting to think that it's the land masses moving around that close the oceans. That it was a northward movement of India that destroyed the Tethys. But actually it's the exact opposite. It was the Tethys that pulled the continents together, destroying itself in the process.
It was subduction that built Eurasia. And it's subduction that's shaping its ultimate destiny.
For 300 million years, subduction has been gradually, inexorably closing the Tethys, creating Eurasia. And as time goes on, it will close the Med too. Africa will continue northwards. This whole area will emerge as land, and these islands will be the peaks of the Mediterranean mountains, a great mountain chain at the heart of a new supercontinent.
As Africa ploughs northwards, France and Germany become ever more mountainous. And those peaks would look out over a vast desert, covering the whole of Central Europe and Asia.
It's thought that 250